Okay, so the title is Psychometrics for Automatic Speech Recognition. And the question is essentially, do modern sort of deep neural network-based models of speech recognition provide a good model of the human auditory system? Now, why would you even ask that question? And is the answer yes or no? That's basically what I'm going to try to get at with this talk. So to get to the first part, why would you ask that question? Why would anyone think that automatic speech recognition might be a good model of the human auditory system? So the context here is that there's been a huge growth recently in using deep neural networks as models of the brain. And there are some good reasons to think that they might be. In particular, you can see lots of similarities between the way they operate and the way we think, or the way we measure that systems in the brain work. So a lot of this started with Dan Yemin's 2014 paper, where basically they trained, this is a vision paper, not a hearing paper. They trained deep neural networks to perform natural sort of image classification things, sort of task. And then they found that you could take the different layers of those networks and use it to predict the activity of measured neurons in, I think, IT and V4 in this case, to novel natural stimuli that hadn't been seen before. So that seems like in some way, quite a strong indication that these models are, despite having never been trained on any neural data, but purely on the task, they somehow found some solutions which are similar to what brains are doing. A little bit later, we have a similar attempt, a similar approach by Josh McDermott's group, the SCALE 2018 paper, did the same sort of thing, but for hearing, they trained a deep neural network at various auditory tasks and found that you could sort of predict, again, various aspects of measured responses. I think in this case, it's some fMRI stuff, but they also predicted some other types of properties. Okay, so that's just a couple of examples, but generally, like, these models have now been so successful that there are now quite a lot of papers arguing that essentially now we have to give up the old way and everyone should just be doing deep neural networks, and that's the only thing that is of any interest whatsoever. So I think that these are very exciting. There's a lot of promise to these methods, but it also pays to be a little bit cautious and not get too much on the hype train with these things. So I just want to point out some of the differences as well. One that, if you haven't seen it before, is I think quite entertaining, at least, is what's called adversarial images. So just as an example of this is a sort of image recognition network. You show it this picture and it says, oh yeah, that's a panda. I'm about 60% confident that's a panda. But it turns out that you take this image, this random noise, or seemingly random noise, you add it, multiply it by some small value epsilon, and you add it to this. You get this image on the right. Can't see the difference between these two images, like basically look exactly the same. And now the deep neural network says that's a gibbon, and I'm 99% sure it's a gibbon. So this is not something we would expect people to do. So this suggests that actually there's something rather different about the way these neural networks are working than the way animals are working. And actually, this is a kind of a general property of these networks, is that they don't seem to generalize well outside of their training data. You train them one set of data, you test them on something slightly different, and suddenly the performance is terrible. They do all sorts of weird things. So the approach that I would like to take to sort of decide, are these good models of the brain or not, is to say, basically, if we're imagining that these deep neural networks are somehow using the same mechanisms as the brains, then if we start creating manipulated sounds, in this case, we ought to see the same sorts of errors. We should see the similar sort of patterns of errors being introduced by different manipulations. Okay, and so that's what we tried to do with this study. All right, so this is sort of going to be a little diagram of basically how we did that. We're going to have sort of models and tests and people. I'll get to that in a sec. So we used three, what were, at the time that we did this, it's probably changed since then, sort of state-of-the-art deep neural network models of speech recognition, with the limitation that it had to be ones that we could actually get access to. So there are better ones that we can't get access to. So the first one is this CalD one. So the architecture of this model is a deep neural network with a hidden Markov model behind it. The input features it uses are MFCCs, mel frequency capture coefficients, which is sort of standard. I imagine probably someone has talked about this at some point already here. Standard input features to sort of speech recognition tasks. And it's supposed to be somewhat related to the sort of features we might imagine people are using, although not terribly similar. But anyway, it's very common in speech recognition literature to use these MFCC features. One thing I would just say about this, if you don't know about it, is that they are based on essentially windowing the sound into little bands of some number of tens of milliseconds. I can't remember off the top of my head exactly. And so they discard a lot of temporal information. They're more spectral than temporal. The next one we used is Mozilla Deep Speech. This also uses these MFCC features, but the architecture of the deep neural network is a long short-term memory LSTM model. Until fairly recently, this was considered the sort of like the state of the art for sequential data. Yeah, okay. And then the last one is, well, the date of this one is more recent, but this is a more recent architecture, is this WAV2VEC model. This one is different in that it takes in raw audio samples as its input. So you don't bake in the idea that it has to be MFCCs. You take raw audio samples, and potentially it could therefore be using temporal information. So it kind of has access to more information than these do. The architecture is also different. It uses a convolutional neural network followed by a transformer. So if you haven't been following the sort of deep learning literature much, I'll just say one thing about transformer, which is that it has basically completely taken over the whole field of machine learning over the last couple of years. Everything is transformers or something to do with transformers now. There's a huge amount of hype about these. If you've seen the examples of like the large language models like GPT-3 and things like that, that can sort of generate plausible sounding text, that's all coming from transformers. Yeah, it's basically the sort of big thing in machine learning. The interesting thing about it is I think that it basically builds in a model of attention. That's what it adds over other previous models, which I think is quite interesting from a sort of neuroscience perspective, because, you know, we also do attention. So, all right, so those are the models I used. And we came up with a set of manipulations of sounds for which we have human sort of psychometric data. So I won't talk through all of these right now. I'm just going to talk through a couple of these because half an hour is not very long. And also if I just kept talking, it might at some point get quite boring. But basically we have a bunch of different sort of tests for which we have human data, and then we can compare. All right. So I'm going to talk about some of the results. Does anyone want to ask a quick question at this point, or shall I wait to the end for questions?
Our transform is very similar to a technical network. The same sort of thing. It's actually not
They're a little bit more complicated, but they have a model of attention built in. But there's some particular details about the way that they use that made them particularly interested. Yes. Yeah. Yes.
That's fixed, is it?
Well, I mean, you can put more in, of course, but yeah, these ones that I'm showing, I mean, they've got, each one of these has a fixed architecture, but you could add more layers and then retrain them or whatever. It's typically quite easy to do that. Like you can fiddle around with these quite a lot, and you tend to get quite good results. In terms, what, by adding more and more layers? That's a good question. I don't think it's always the case that adding more layers always gives you more performance. But I would have to check on that. I'm not 100% sure off the top of my head. Typically what they do, and these big companies can afford to do this, is they run this training with every possible architecture that they can afford to run, which is a lot, and certainly more than any academic can do, and then just show you the results for the best one. And they're a bit cagey about what exactly was involved in that. So it's a bit difficult to know exactly how it depends on all of those details, because they don't really want you to know. Cool. Okay, I'll continue. All right, so the first one, quite a simple one, is just if you start bandpassing these sounds, like for example, you might do if you're listening on a phone, and you know it gets rid of quite a lot of the frequency range to be able to compress it more. You train your models on clean speech, but then you test them on speech that's been bandpassed. And this here is the range of that bandpass filter. So going from very narrow to quite wide. It cuts off at 8K because I think some of the models couldn't use information above 8K. So we just, to try and make it fair between everything, everything was cut off at 8K. All right, so you can see, first of all, that humans are much better than the speech recognizers, right? So very quickly, with about 10-ish semitones, they reach pretty much perfect performance, whereas it's taking many, many more semitones before these models start to get reasonably good. You also see that of these different models, the CNN transformer architecture is the best. And that's something we're going to kind of find across all of these tests. So I just wanted to highlight that at the beginning. Okay, so all right, so that's just, first of all, yeah, you also tend to see this pattern is that humans do better. And in a way, that's not necessarily that much of a problem. Like, humans are doing potentially much more stuff than all of these algorithms are doing. So we shouldn't in some way necessarily penalize it just for doing worse. It's more going to be, I think, about the pattern of the errors that tells us whether it's potentially a good model. Okay, so second experiment is about clipping. So on the left here, we have peak clipping. So that's basically if the sample goes above the maximum that you could record, it gets clipped to that maximum value. Basically, that's what you get if you set the levels on your gain on your microphone wrong or whatever. And on the right is center clipping, and that's basically where if the pressure goes below some value, it gets set to 0. And that's something you might see in some sort of, now probably quite old-fashioned, but noise reduction systems. So it's two sorts of manipulations of the data of the sound that are somewhat reasonable to do. So again, we see that particularly for this peak clipping, humans do much better than the speech recognizers, and the speech recognizers really not showing a particularly similar pattern of error here. They're going down to virtually 0 performance, whereas humans are doing quite well. This particular point here is kind of amazing, which is that if you take every sample and you just replace it with a +1 if it's positive and a -1 if it's negative, humans can still hear quite well. I mean, that's kind of impressive. Sorry? Pretty much, yes. Yeah, exactly.
You can still apply 0 positive signals into those loudspeakers and speech.
Yeah, yeah. Yeah.
So these networks, speech set, right? That's, can you talk a little bit about speech and noise? And
yes, I think they're mostly being trained, as far as I know, all of these are trained on clean speech.
Okay. How do we know what their performance is for speech and noise?
Yes, not as good as humans.
Right. Contrast obviously with some other networks, some speech recognition, some deep neural networks now, which are pretty much as good as humans. I like that. Some instances better than humans are doing speech and noise.
Not for any of the ones, at least, that are open, as far as I know. There may be some proprietary ones that are doing that, but I don't know about that. I'd be interested to hear about that.
The Crow stuff is an example. It wasn't the same kind of speech recognition, I can't remember. My recollection was that their speech and noise performance of their networks would be much matching human.
Well, I've got, I can show you at the end, I've got a slide for when you've got competing speakers. So I can show you that for these networks at the end. Yeah. Cool. Okay. So, all right. So for this peak clipping, they don't do as well as humans. But interestingly, for the center clipping, at least 2 of the algorithms actually are doing very comparably to humans. So the CNN transformer and the hidden Markov model are both kind of doing something quite similar to humans. So it's not just uniformly that these networks are doing bad. It's that the pattern of where they do well and where they do badly is different, right? So, doing quite well in this center clipping, but really badly in this peak clipping, that suggests that there's something different underlying going on. All right, so I'm going to talk about this one. I don't know how well everyone can see I wanted to get all of this figure on, but it's probably a bit small at the back, perhaps. This one take a little bit more talking through. So this is about temporal fine structure. So what we have here is we basically manipulate the sound to remove all the TFS, the temporal fine structure, and then we start putting it back. And we either start putting it back starting at the low end, that's this orange curve, or at the high end, and that's this yellow curve. And this is speech reception thresholds, so lower is better. And basically what you see is that as you start adding it in, you go from slightly worse performance to slightly better performance, either starting at the high end or starting at the low end. And what you'll see is that for humans, that's this column here, you get a big benefit from having the TFS. So that's like 9 or 10 dB benefit, something like that. However, you don't see the same improvement for these speech recognizers. So this is the CNN transformer, this is the hidden Markov model, and that's the LSTM. Much smaller benefits, almost nothing really for these ones, like very little benefit of putting the TFS back in. In this case only, perhaps you're seeing a little bit of benefit, but even then, it's not so much.
Sorry to two networks on the right don't have access to these systems, do they?
Not directly, although you're doing a manipulation of the sound, which will change lots of features of it, right? So they are behaving differently. But yes, indeed, they don't have the raw samples, so they have some echoes. Exactly. Yeah. But yes, good point. Yeah. Not too surprising. Okay, so again, in this one, but the transformer does, right? So it should in principle. In this one, what we have is we have essentially like the benefit of basically having envelope or envelope plus TFS is basically the difference between these. So again, for humans, we're getting a sort of consistent benefit from doing that. And for all of these models, you can see basically there is no difference at all by whether or not you've included that TFS information. Okay, so again, same thing that you're seeing a sort of consistent difference in the types of errors that it's making. I should also mention, by the way, that this slightly elides the fact that the thresholds are very different. Here you can see that they're in the sort of -10 to -18 range, and here they're the +8 to +16 range. Yeah, otherwise this plot wouldn't look that nice. Good. All right. So one last, I think this is one last before I get to my conclusions. Yeah. So here we're now looking at the benefit of introducing periodicity or fluctuations in a masker. So what we see here at the top is with periodicity, and at the bottom with fluctuations. And in both cases, we have this column. It's with a periodic vocoding, Dudley vocoding, and noise vocoding. Okay, just three different ways of doing this essentially. And what you see in all of these pictures is that humans are able to make use of this information. So if there's some periodicity or some fluctuations in the masker, humans do better. And you also see that the CNN transformer is also doing better. So in this case, very similar to humans. In some other cases, it's getting a benefit, but maybe not quite as much as humans. But it seems in all cases to be able to make use of this sort of information. The DNN and the HMM and the LSTM model are really not able to make use of this. And in fact, in some cases, thrown off by it so much that they actually start doing worse. Yeah, okay. So that was just like three of our experiments. Please do feel free to ask or read the paper. There's a lot more. It's a really long paper. I apologize if you do read it. But I didn't see any way to avoid that. But yes, just to give an idea of that, and now I'll try and summarize some of that and give some conclusions based on that. How am I doing for time? Okay, I'm good for time. Okay. All right, so first of all, speech recognition still seems to be much worse than humans, particularly when we start putting distortions in. They also seem to mostly be making different sorts of errors than humans. So does that mean that they're using different mechanisms? I would tend to say probably yes. And it's not just a matter of throwing more data and more computing power, more parameters at these things. The architecture seems to matter. I think most of these models were trained with somewhat similar amounts of data, but what difference between them is their underlying architecture. And none of them seem to exploit temporal fine structure, even if they could, which is also kind of interesting. The CNN transformer ones seem to be generally the closest to humans, and so that maybe makes us ask the question why. It's not because it's exploiting temporal fine structure. That was sort of initially our guess, is that because it could exploit temporal fine structure, it might do better, but it doesn't seem to, so that doesn't seem to be the reason. We don't know exactly why it's doing better. One possibility is that MFCCs are not good features. What this one does is we have some unsupervised pre-training directly on raw audio, and maybe it finds a better feature set than MFCCs. It could be just as simple as that in some way. And it could be that the attention mechanism is actually is important and is a similar mechanism to what humans are using, and therefore that explains some of why it's doing better. We've released all of our code on GitHub. If you want, and you have a different sort of psychometric test that you want to try out, it's quite easy to do. If you have a different automatic speech recognition model that you want to try out, it's easy to do. You can just add it to this package and it will generate all of these plots. And so you can do these sort of side-by-side comparisons. Okay, well, thank you very much. That's Lotte, who was supervised by Claudia, who's at Imperial, and Stuart was great with lots of advice on this project. Great, thank you very much. Thank you.